All right, let's go through some tutorial questions. The first question here says, which of the following is not a use of transistor? Before we answer this question, we need to recall all we know about a transistor. The option here says collector. Transistor is not used as a collector, is not used as, that is A. B says switch, C amplifier, and D logic gates. Now, a transistor is a semiconductor device that can act as switch, can act as an amplifier, it can act as a current regulator in electronic circuit. Now, among the options here, I have not mentioned collector and logic gate. Logic gate, fine. Transistor can also be used as a logic gate, that is through IC. The collector is just a terminal in a transistor. We have 3 terminals in a transistor, which are the base, the collector, and emitter. So collector is just a terminal, so it can't be an application of a transistor. So the right option is A. Transistor cannot be used as a collector, but it can be used as a switch, can be used as an amplifier, can be used as logic gates. Now, question number 2. N-type semiconductors are now, again, the options are there: A, B, C, D. A, negatively charged. B, produced when indium is added as an impurity to germanium. C, produced when phosphorus is added as an impurity to silicon. And D, none of the above. We know that an N-type semiconductor is a material with an excess electrons, which gives it a negative charge. But that does not mean that the N-type is just negatively charged. Semiconductor materials have dual charges, electrons and holes. So when you say it's negatively charged, it means that there is no hole, only electrons. So A is wrong. B, indium is group 3. Group 3 element adding to semiconductor material impurity. Group 3 material or impurity adding to a germanium semiconductor material cannot, rather it will create a hole, because for a semiconductor material, they have 4 outermost electrons, 4 electrons in their outermost shell. 4 electrons in the outermost shell. So if 3 electrons are supplied or provided, that would be 7. So there will still be 1 space left. So it will not give you N-type, rather it will give you a P-type. Now, C, option C says, produce when phosphorus. Phosphorus is group 5 element. So if the 5 outermost electrons is added to silicon, which has 4 outermost electrons, 4 of the phosphorus will go into bonding with 4 of the silicon electrons, and then 1 electron will be excess. So that 1 excess electron is what makes the semiconductor material to become N-type. So the correct answer is C. Correct answer is C. Then question number 3. Question number 3 says low input impedance and high input impedance in a transistor implies A, low input current, low output voltage, high voltage gain, low voltage gain. Now, a transistor with a low input impedance and high input impedance indicates that it is most likely configured in a common base amplifier circuit. So this configuration allows for a small input current to control a large output current, making it suitable for high frequency amplification with low input loading. As such, the correct answer should be C, high voltage gain. High voltage gain, C, is the correct answer. I'll move on to 4. A transistor can be used as, just like the first question we answered, it can be used as, and the option says oscillator and switch, oscillator and amplifier, switch and amplifier. Yes, we know that transistor can be used as oscillator, that is, to convert DC signal to AC signal. And then transistor can be used as an amplifier by amplifying small signal, making the small signal to be a large signal. And then the next one, which is switch, when transistor is operated in saturation mode or cutoff mode, it could be used as a switch. So the correct answer is D, all of the above. All of the above. Question number 5. The barrier potential of a certain semiconductor junction is 0.7 volt. What material is the semiconductor made from? What material is semiconductor made from? Now, there are 2 types of semiconductor material. We have germanium and silicon. The barrier potential is the same as the PN junction. So at the PN junction, the voltage so the barrier potential is the same as PN junction. Barrier potential is the potential difference across a PN junction that opposes the flow of current. When the barrier potential increases to a particular level, it prevents current from moving across from the emitter junction to the collector, or the base side to the collector side. Now, for any current to move across from the input to the output section of the transistor, it means that there is a threshold voltage that must be supplied. Threshold voltage. So for silicon, that threshold voltage is always 0.7 volts, while for germanium, the threshold voltage, which we can also call the barrier potential, is 0.3 volts. So it implies that from the question, the material used for such semiconductor is silicon. Silicon. C. And the next question, which is question number 6, says when the input section of a transistor is forward bias and the output section is also forward bias, the transistor is said to be operating in A, common base mode, active region, common emitter mode, and saturation region. Now we have 3 modes of operating a transistor. We have the active mode, which is when the input section is forward bias and then the output section is reverse bias. And that is the configuration or operation for amplification. Now, that is when we want to amplify a signal, we ensure that the transistor is connected in active mode. Input forward bias, output reverse bias. Now, when the input and the output are both reverse bias, that is referred to as cutoff mode. In that mode, the transistor serves as an open circuit. That is an open circuit, which is off mode in a switch. Then if we configure the transistor in a way that both input and output section are forward bias, that is the saturation mode. And that is when the transistor acts as a short circuit. A short circuit. And in that circuit, in that form, the transistor acts as a switch that is on. So the correct answer is a D, saturation region, because both input and output are forward biased. All right, so let's move on to the next question. Sorry. Question number 7 says, in a common emitter configuration, the output section consists of the A, collector junction, collector base junction, emitter collector junction, and base emitter junction. Common emitter configuration. So common emitter configuration implies that the emitter is common to both input and output. The emitter is common to both input and output. So if the emitter is common to both input and output, the question is, which terminal is at the input and which terminal is at the output. So let's draw a circuit like this. So this is emitter. This is the base, and this is the collector. Emitter E, collector C, and base B. So this is a common emitter configuration. So in that case, this is the input, while this is the output. So the base emitter is the input, while the collector emitter is the output. So the correct answer to this question is C. That is emitter collector junction. Emitter collector junction becomes the output section. Right. So let's move to the next question. A transistor in saturation. A transistor in saturation. Now, a transistor in saturation is in its own mode and acts like a short circuit between the emitter and the collector, like I explained before. It means that the switch is on because it is in on mode. The switch is on. If the switch is on, imagine you just think of your home where you have a switch that controls your light or your bulb or your fan. If the switch is off, what will happen? There will be no current flowing to the bulb or to the fan. So it won't power it. And the fan will not work, the light will not come on. But if the switch is on, current is allowed to flow through it. Current is allowed to flow and then go up to the bulb to power it, or to the fan, or whatever appliances you want to power. So from this question, the transistor in saturation, the correct answer should be A, because it says is passing maximum current through the output. A should be the correct answer. Maximum current. Current is allowed to flow through the output. Of course, it's at the output that our load, our appliances are connected. So current is allowed to flow through the output. So let's move on to the next slide. Okay, this is calculation. If the collector current changes from 2 milliamp to 5 milliamp in a transistor when collector emitter voltage is increased from 2 volts to 10 volts, what is the output resistance? So the first thing is to write out the relationship or the formula that relates them. Output resistance, that is small r naught is equal to change in voltage VCE over change in current IC. So since the change in current means change in voltage over change in current. So we have two voltages, we have two currents. So the change in the voltage will be 10 minus 2, 10 minus 2, which is 8. And so R naught is equal to 10 minus 2, which is equal to 8. And then change in the current with 3 milliamp. 3 milliamp is 0.003. So that will give us 8 divided by 3 is that's 2.6 B67 kilo. So the correct answer is C. The correct answer is C. The next question, that is question number in a IC 6800 microamp. The emitter current, IE, is 30 milliamp. And is 12.5 volts. Is current amplification is input current over input current. For a common base, it implies that the input current is I, E, while the output current is IC. So alpha is equal to output current IC over input current IE. So the output current is 6,800 microamps. So it will convert that to milliamp. That will give us 6.8 milliamp over 30 milliamp. So the unit will cancel. This will give us 0.02. 0.02. So the answers here are wrong. The correct answer should be 0.02. 0.02. That should be the correct answer. So move on to the next question. Here we are given in a transistor IB, that is the current flowing through the base. The base current is 68 microampere. The emitter current is 30 milliamp, and beta is 440. Determine alpha rating of the transistor. Beta is amplification factor. So we are asked to find alpha rating of the transistor. In the previous one, we had alpha is equal to IC over IE. Now, IE is not given. So how do we get IE? Okay, IE is given, sorry. IC is not given. So we need to solve for IC before we can get the amplification. Now, for this kind of configuration, beta is IC over IB. IC over IB, which implies that IC is equal to beta IB. So beta is 440. IB is 68 microamp. So let's convert the microamp to milliamp because of the IE, which is in milliamp. So we have IC becomes 440 times 0.068. 0.068. That will give us 29.92 milliamp. So our IC is 29.9 milliamp. So if we come back to the IC over IE and substitute 29.92, which is approximately 30 over 30. So that will give us alpha as 0.99. You know that the value is approximately 30, so almost 1. But we are not going to approximate it. We'll leave it the way it is. So our answer is 0.99. No unit because they are both current. So our correct answer is D. Our correct answer is D. The next question, in a common base transistor configuration, IB is that IB is 6,800 microamp. IE is 30 milliamp, and beta is 440. We are asked to find IC. So to find IC, beta is equal to over IB, which implies IC is equal to beta IB. That is 440 times 6.80. 6.80. 440 times 6.80. So that will give us, let me use the calculator, 440, 440 times 6.8. Okay, so let me take it to, instead of 6.8, convert it to ampere. Convert the 6,000, 6,800 to ampere. That would be divide by 10 raised to 6. Divide by 10 raised to 6. So that would be 0.068. So we have 1, 2, 3, 4, dividing by, so our answer is 2.9. 2.992. Okay, so there's a mix up here. So what we should do is we should just go straight to this formula. IE is equal to IB plus IC. IB plus IC. IE is given, IB is given. So to get IC, that will be IE minus IB. So that will give us the right answer. So IE is 30, 30. IB, if we convert 6,800 to milliampere, that will be 6.8 milliampere, because IE is in milliampere. So that gives us 23.2 milliampere. So the correct answer is C. So C is correct. C is the correct answer. So let's move on to next. Here we are asked to find the base current for a common emitter connection, provided with the beta for a transistor beta is equal to 45, and the voltage drop across a 1 kilo ohm load, which is connected in the collector circuit, is 1 volt. Find the base current. Find the base current. So how do we go about this? The first thing to do is we need to find the collector current. So we have VC and the load resistance. So IC is equal to VC over RL. RL is the resistor at the collector section. So they are both, this is 1 over 1 kilo ohm. So that will give us 1 milliamp. So IC is equal to 1 milliamp. But it's not IC we are asked to find. We are asked to find the base current, which means we have to use the amplification factor to find the base. The amplification factor beta is equal to IC over IB. IC over IB, which means that IB, which is the base current we have to find, will be IC over beta, which is 1 milliamp over 45. 1 milliamp over 45, that will give us 0.022 milliamp. So the correct answer is C. C is the correct answer. The next question is for a transistor, beta is equal to 45, and voltage drop across a 1 kilo ohm load, which is connected in the collector circuit, is 1 volt. Find alpha. Alpha is current amplification. Alpha is current amplification. That is, alpha is equal to IC over IE. IC over IE. So previously we solved for IC, and is IC, we solved for IC to be 1 milliamp. That is, IC is equal to VC over RL. VC is 1 volt, and RL is 1 kilo ohm. So that is 1 milliamp. Now, we are given beta, but we need to find alpha. It's alpha we are asked to find. So what we should do now is, we have beta, we have IC, we need to find IB. So if we take the relationship beta is equal to IC over IB, it means we can find IB to be IC over beta. So IC over beta will give us IB, and that is 0.02 milliamp. That is 0.02 milliamp for IB. Now we have IB. We have IC. So we need IE to be able to find alpha. IE is equal to IC plus IB. IC is 1 milliamp. IB is 0.02 milliamp. So I E will be 1 milliamp. 1.0. So alpha will be IC over IE. IC is 1, 2. So that will give us very close to 1. So our answer is 0.98. No unit because it's current over current. So the answer is a D. The answer is a D. So let's move again to the next example. Example, transistor. Calculate beta. Alpha is given as 0.5, calculate beta. There is a relationship between alpha and beta, and that is 1 minus 0.5 is also 0.5. So we have beta becomes 1. So the correct answer is B. The correct answer is B. Example, exercise 16. For a transistor, beta is equal to 45, and the voltage drop across a 1 kilo ohm load, which is connected in the collector circuit, is 1 volt. Find the collector current for common emitter connection. We've done this before. IC. We are asked to find IC. IC is VC over RL, which is 1 over 1 kilo ohm. So IC is equal to 1 milliamp. So the answer is A. The answer is A. So we move to exercise 17. If a transistor is connected in a common emitter mode, and VCE, that's voltage drop across the collector emitter junction, is 8 volts. If beta is 24 and IC is 0.625 milliamp, calculate IB. Beta is IC over IB, which implies that IB becomes IC over beta. So IC is 0.625. Beta is 24. Sorry. Beta is 24, not 25. So 0.265 divided by 24 will give us 0.026 milliamp. So the correct answer is for 17 is A. The correct answer for 17 is A. Now for question number 18. If beta is 24 for a given transistor, calculate alpha. So there's a relationship between beta and alpha to solve similar question. This time, alpha is equal to beta over 1 plus beta. I remember that beta is equal to alpha 1 minus alpha. So if you simplify this and make alpha the subject, you have alpha to be beta over 1 plus beta. So beta is 24, 1 plus 24, 1 plus 24. That is 24 over 25, very close to 1. I'm looking at it. So our answer is 0.96. So A is the correct answer, 0.96. A is the correct answer. So move to, we are going to treat 20 questions in this first part. Ensure that you subscribe so that by the time I send subsequent tutorials, you'll get the prompt and just go through them. Question 19. A transistor is connected in common emitter mode, in which collector supply is 8 volts and the voltage drop across the resistance X connected in the collector circuit is 0.5 volts. The value of X is 800. What is the collector emitter voltage? Collector emitter voltage. Now, this kind of question, if you look at it very well, it's like asking you, okay, it has to do with the difference in the junction of the collector emitter, collector emitter junction. So we have the supply voltage is 8 volts, and then at the junction we have 0.5. So the difference between 8 volt and 0.5, that is what you just need to know. That is 8 minus 0.5. We give us a collector meter voltage. It's a junction voltage. One of the questions asked about that has to do with the threshold voltage or the barrier potential for silicon is 0.7, and then for germanium is 0.3. So this is a similar equation that is very close to that. So if the voltage is at the barrier potential is 0.7, you will need a voltage that is equal to greater, a voltage that is greater than 0.7 for current to begin to flow across that junction. Any voltage you supply that is less than that threshold voltage will not power the system or will not enhance current to flow across the junction. So here, the junction voltage is what is required, and that is 7.5 volts. B is the answer. Then, okay, this has to do with Fermi energy level. The probability that an electron in a metal occupies the Fermi level at any temperature greater than 0 Kelvin is. So this question has to do with energy band. Remember that we have basically 3 categories of material. We have semiconductor, we have the conductor, which is we can say metal, semiconductor, and insulator. For conductor, there is no distinct gap between the valence band and the conduction band. They overlap because the electrons in the conductor, they are XX and they move around randomly from one point to the other. While for semiconductor, they behave as a conductor when the temperature is above room temperature, and behave as an insulator when the temperature is 0 degrees. And so the gap for a semiconductor is small, narrow, but for an insulator, the gap is wide. So here we are asked the probability that an electron in a metal occupies the Fermi energy level at any temperature greater than 0. So whether greater or less than 0, the electrons will always be in both conduction and valence band. But the questioner is asking, what is the probability of electron in that band? So we write F of E is equal to 1, that is the formula. You have to know this formula. 1 plus exponential E, which is the energy level of the electron, minus EF, which is the Fermi energy level, all divided by KT, K for Boltzmann constant and T for temperature. So like I said, for metal, which is a conductor, the conduction band and the valence band overlap, which implies that the energy level is equal to the Fermi energy level. E is equal to EF. So if E is equal to EF, it implies that we are going to have 0 here. The exponential E minus EF will give us exponential raised to 0 because E minus EF will be 0 since they are equal. So we are going to have 1 over 1 plus exponential raised to 0. Anything raised to 0 is 1. So that gives us 1 over 1 plus 1, which is 1 over 2. And that gives us 0.5. So our answer will be C. Our answer is C. So we'll stop here for today, and then the course, other tutorials. So don't forget to subscribe